So we're transitioning to smell, and what we talked about before this lecture was taste, and we described how they're very closely related. And hopefully you remember that. We gave examples of when you have a head cold, food doesn't taste so good because your sense of smell is usually compromised. We talked about the different regions of specialization on the tongue. Not that, I think there's music playing. That's very interesting. I don't recall playing any music. I think this computer's possessed. Yeah, it's because I turned the volume off. It's still playing, but it's more like background music. Okay, a little bit of elevator music for the lecture, put you to sleep. So we talked about the link between taste and smell. Olfaction is what we call smell. And where we had about 10,000 receptors in the mouth or the oral cavity, here we have orders of magnitude larger. We have 10 to 20 million receptors for olfaction or for smell. Now these are organized very similarly as they are in taste, and we're going to talk about that. And like what we saw with taste, in order to detect or discriminate a certain odor, that is tied to a chemical. And that chemical has to be dissolved. And it's dissolved in solution in the nasal mucosa. That's why the nasal epithelium is moist. And you can see examples of other species, like your family dog, okay, that has a much more keen sense of smell. And their nose is always moist. Okay? And that helps to make sure that those odorant molecules become dissolved very, very fast, as soon as they come in contact with the epithelium. If we look at the architectural arrangement that's shown here, you can appreciate this is our olfactory tract, this is our olfactory bulb, and through, what bone is this? The ethmoid bone, very nicely done. And there's holes, and those holes are called what? You guys remember those holes? What's that? Foramen? That's a good guess. It was called a cribriform plate. You guys remember that? And that actually is a part of the ethmoid bone that has all of these. It looks like a colander. And the reason for that is for these olfactory nerve branches to be able to dive down. So we have our olfactory cells, which are actually neurons, as well as the epithelium that's supported by supporting cells that we'll look at here in just a moment. And we have basal stem cells that give rise to new cells, just like what we saw with the taste cells. These have a lifespan of about 60 days. And we've got them located in the mucosa of our superior conch, nasal septum, roof of the nasal cavity, which is about 5 square centimeters in surface area. And so the human has the ability to discriminate 20 to 40, or 2,000 to 4,000 different odors. So instead of maybe a handful of different tastes, we have upwards of 4,000 different odors that we can discriminate with our nose. So now you can appreciate if you have a meal and there's a certain flavor to it, it's not just as simple as a salt, sweet, bitter, sour, or meaty umami flavor. Right? There's all sorts of things in between, and that fine-tuning happens here at the level of the nose. Question in the back.
So, in general, people who get frequent nosebleeds and have the procedure done in their nose where it's, I think it's like burned on the inside.
Cauterization of the epithelium?
Do they have a hindrance sense of smell, if any
Well, I would imagine on the surgical form, one of the risk factors associated with that surgery is a loss of olfaction. So you probably signed that you recognize that this procedure may compromise certain ability to smell, or maybe smell goes altogether, right? So you guys have all seen those forms, and that's probably what, side effect, loss of discrimination of odors, sense of smell, maybe complications with taste, and death, right? Everything's like, and death, right? Pretty soon you can go get your nails done and be like, and death, right? So that's probably on the form, okay? All right, if we look at these olfactory cells, the cells themselves are the neurons. They look like little bowling pins. They look like little bowling pins. And that's what you're seeing down here are these little bowling pin-like structures that are showing up. Okay, they're colored in sort of this orangish-like color. That's the olfactory cell. And next to it in purple are the supporting cells. And then the basal cells are found at the basement membrane, right here. And they divide and give rise to new olfactory cells about every 60 days. So about every 2 months. The head itself bears 10 to 20 cilia, and these are called olfactory hairs. And they have binding sites for the odorant molecule. And those hairs are non-modal. The olfactory hairs are not for motion of any sort. They're for actually binding the odorant molecule. And these are not those are not the hairs that old men trim post 60 years of age. You guys know what I'm talking about, right? It stops growing in certain places and it starts growing other places. But that's not what you can't see these. These aren't hairs that are coming out of the nose that are trimmed, the little nose trimmers. Okay? I get that question from students, like, so, like, is that like what I see in my grandpa? It's like, no, you're not seeing these. Because they sit in a tangled mass and they lie in a thin layer of mucus. And what's the importance of the mucus? Give me some functionality of that mucus. Absorb the odorant molecule, allow it to dissolve. What else? Debris, dust, particulates, captures that. Okay? It also helps to moisten and warm the air as you inhale, if you inhale through your nose. Because that thin layer of mucus obviously is moist, and it's body temperature. Okay, so that actually conditions the air before it moves into the respiratory tract. Bless you. If we look at the olfactory cells continuing, the basal end of each cell becomes the axon. So these guys are like extensions of the nerve. These are the only nerves that are exposed to the outside environment. That's different than what we found in the mouth. Okay? The axons collect into small fascicles and they leave through the cranial cavity in that cribiform plate. And this is a cross-section, and you can see and appreciate these holes in this cribiform plate of the ethmoid bone. And then as you get back up here onto the bulb itself, you have a series of synapses that transmit the signal. Every synapse, there's a neurotransmitter, just like what you would expect. We're not going to get into the details of which neurotransmitters, but you understand the general property now of how this works. Odorant molecule binds here. That's a chemoreceptor, right? That chemoreceptor triggers a channel to open. A positively charged ion flows in. That stimulates an action potential. And it goes all the way through the bone. There's a hole in the bone that you probably studied in lab. And it synapses onto this first glomerulus. And it synapses onto what we call tufted cells, then mitral cells, and eventually onto the olfactory bulb. We're not going to study which synapses have which neurotransmitters, but I want you to be able to appreciate, okay, This is just a standard action potential like we've been talking about for much of the semester. The fascicles that collect back here on the olfactory bulb collectively make up cranial nerve number 1. That's the olfactory nerve. So as I mentioned, these are the only neurons in the body that are directly exposed to the outside environment. Because the taste cells that were found in the taste bud, those guys had a synapse at the back end, the basal end, and there was a neurotransmitter that went over, okay, onto the nerve. These guys in the nose, the olfactory cells in the nose, are actually part of the neuron itself. And the olfactory hair is an extension of that nerve, and that's what the odorant molecule binds to. So they have a lifespan of about 60 days. The basal cells divide. They're the stem layer, right? Basal cells is sort of a standard terminology. We saw stratum basale layer of the skin, right? We saw basal cells in the mouth, in our supporting structures around our taste cells. And here we see basal cells again in olfaction. So that word should be very familiar to you. The supporting cells, they provide a nutritional environment for the olfactory cells, but they don't have any olfactory role. So as humans, we have a rather poor sense of smell, compared to a lot of other mammals. Women, it's been well described, have a more sensitive olfactory capability than men. And of course, olfaction is highly important to social behavior in the mammalian kingdom. Okay, it looks different depending upon the social interactions of that mammal group. And you can see that within humans versus with dogs or other mammals. Okay, but smell makes a huge difference. Your family dog, all kidding aside, but they determine individuals based upon odor, more so than they do vision. And so that's why when you come home, they're always greeting you by smelling. Okay? Or somebody new walks in the house and they're always goosing people because there's glands, right, in the crotch that actually give off an odor that's very unique to you. And so they know if that person has ever come to your apartment or your dorm room before by the way they smell. Now, in the human world, we just shake hands and introduce each other by name, okay? Which is a little bit more, civilized, apparently. But the sense of smell is a huge deal within the mammalian kingdom. These odorant molecules, they bind to the membrane receptor in the hair. In some cases, if the odorant molecule is hydrophilic, it can diffuse through the mucus layer. Hydrophilic is a word that means water liking. If it's hydrophobic, that's the phobia of water, water fearing, it actually has to be transported by an odorant binding protein through the mucus, which is kind of crazy that it's that complicated just to smell. Now all of these, when they bind on the other side, they activate G protein and cyclic AMP systems, so you know that they're not necessarily depolarizing the membrane directly. They use a second messenger system. They act more like a metabotropic type of neurotransmitter. You remember that? Metabotropic neurotransmitters are ones that have a cascade of events that take place, and then ultimately it allows for depolarization to take place. And that's how olfaction works. So eventually, once the odorant binds and you stimulate your second messenger system, G protein and cyclic AMP are just two different examples of second messenger systems. Then you allow for channels either for sodium or calcium to open, and it causes depolarization and therefore an action potential. Now, lastly, our action potential travels to our brain. And the olfactory receptors, they can adapt extremely quickly. Okay, so an evidence of this is, I can remember as a kid, I had two brothers growing up, and we'd always decide to roughhouse in somebody's bedroom. We'd close the door and turn the music up so Mom didn't know we were roughhousing, which is more like, mixed martial arts that was unsupervised and, before MMA was fun, popular. As long as nobody broke anything or didn't have to go to the emergency room too frequently, it was fine. But Mom would walk in, right, the door of the room, and she'd walk in. What do you think she would say with three sons wrestling? Huh? It smells. It smells like boys. That's what she would say. I don't know what that means because I have all girls. It's bad. It's bad. So she opens the door and says, "It smells like boys." No, I do know what it means because inevitably somebody like, "Dude, I need to go get a drink." We walk out to the kitchen, grab a drink, open the door, and go, "You guys stink," right? Because when you're in the room, your receptors adapt and reset. And they adapt very quickly. And so it's this sensitivity level that changes with olfaction, which is kind of cool. So this is due to a phenomenon known as synaptic inhibition in olfactory bulbs, allowing it to inhibit that signal if the stimulus is constant, like three boys wrestling in a small bedroom. Okay? But then once you have a reset and you re-enter that environment with the odorant molecules, you trigger those pathways again. Now, some odorant molecules act on nociceptors of the trigeminal nerve. Okay, nociceptors of the trigeminal nerve. Remember, this is the fifth cranial nerve, the trigeminal. And the things that act on the trigeminal nerve to give you some sensations of pain are things like ammonia, menthol, chlorine, or the capsaicin active agent of hot peppers. Okay, and it may cause watery eyes or teary eyes to take place. If you've ever had something extremely spicy, it's not just the nociceptors within the oral cavity. You're also getting that capsaicin pepper stimulating nociceptors in the nose, and that can cause watery eyes and for you to cry.
I was going to ask, what about like a skunk smell? Like you don't get used to, you don't get used to the smell of a skunk if you stay in the room for long enough.
Right? I don't know. I would probably try to get out.
Right, that just made me think of like my high school. Like we always had skunks that would hang around the buildings, and then you walk in and you sit there and you're like, nope, it's not going away.
It's not going away. It's just a super strong odor. So there are certain odors that are overpowering, and there's enough convection in the room where the odorants are moving around, where you are getting different concentrations depending upon when you inhale. So it's still happening, but because it's such a strong odor, and I don't know if we have a lot of skunks in Flag, and my dogs have been sprayed by them numerous times. And like a fresh skunk smells a little bit more like burnt rubber. I don't know if you've ever smelled like right away. You could try this experiment at home if you'd like, and let me know. But it smells more like burnt rubber. And then the stinky skunk smell you get when you're driving down the interstate, you're like, oh, skunk. That's like way old. That's like hours old to days old smell. But the real fresh skunk smells like burnt rubber. Over here and then back over here.
So you said there are hydrophobic and hydrophilic different molecules. Is there a reason why we can differentiate between the two, or at the end of the day, does our brain?
Oh, we can't differentiate between the two. When the odorant comes in, if it's hydrophilic, it diffuses right through. If it's hydrophobic, it just gets stuck in the mucus, and if there's a carrier protein that'll shuttle it across, then it'll shuttle it across.
But there's our brain doesn't care between the two, whether it goes in straight away or if it has to.
No, they're just different odorants that are packaged as hydrophilic or hydrophobic. But the brain, it's not like you smell the flowers, hydrophobic, man. I mean, it just doesn't work that way. It's just the way that the mechanism is transferred. Okay?
Last week you were mentioning that menthol is kind of like a false medicine. It doesn't really do anything, it just feels good.
I said that? I said false medicine?
Yeah, you use that word, but that's just how I interpret it. It makes sense. So like with Vicks Vapor Rub, when you put it on your chest, it can like open up your nose and help you breathe better. So it has to have some sort of like anti-inflammatory response. So
No, it does cause dilation of airways.
Okay.
Yeah. But when we were talking about methyl salicylate, which is the active in icy hot. I was referring to it as a pain reliever. So it's a masker of pain, right? The icy hot is a masker of pain. But it's not fixing anything. It's just masking the pain. But that's what Tylenol does. And in this case, with menthol, it'll actually dilate those airways and open them up. So the Vicks Vapor Rub does work to open up airways. Okay. All right. Other questions? All right, let's move into hearing. And we're first up going to talk about the hearing anatomy. And then we'll get into some of the physiology associated with hearing. This is now our third special sense. So we have hearing and equilibrium, and then our last one is vision. If we look at hearing, the two that we came from before, if we're going to classify those receptors, what terminology would you use? Taste and smell, gustation and olfaction. What kind of receptors are those? Chemoreceptors. Everybody agree with that? How about exteroreceptors? Sure. Do you agree with that too? A and B only? Well, I don't know what C and D are. Let's pretend that they're, as one student said in my office hours, those are obviously wrong, just there to trick me. So let's just pretend that C and D are obviously wrong, just there to trick you. Then that answer would be A and B only, right? You fell into the trap, Keller trap. All right, so here now we're in hearing, and what kind of receptor would you call this? A mechanoreceptor. It's also an exteroreceptor of sorts, because you're getting information from the external environment. No, we're not at equilibrium yet. But yes, equilibrium is. Okay. This is a response to vibrating air molecules, hearing. We're just talking about hearing. Because hearing is a unique special sense, and equilibrium is a second unique special sense. Equilibrium is the sense of motion or body orientation and balance. So this is actually more proprioception, not mechanical. I misspoke. Both of these senses reside in the middle, in the inner ear. And we're going to look at the maze and the passageways that are quite fascinating. When you think about the orientation of the ear and how it's constructed, it's pretty spectacular. The fluid that's within our ear senses the motion. So the analogy for hearing would be, imagine a still pond. Okay? And imagine taking a pebble and throwing it into the still pond. And then you can use your imagination, because you've seen this before, you can use your imagination to see what would happen with those waves as they move across the pond. Okay? You're taking mechanical energy in that analogy, and you're converting it into a wave pattern within a fluid. Okay? So that's how we actually intercept this information, especially about hearing. So the medium that we're in is air. And different mediums are going to allow for different vibrations to take place. Classic example, can you hear underwater? Of course. But you sound totally distorted, right? So you can like yell at your brother underwater and he doesn't really know what you're saying. It's kind of cool, right? And so in space, where there's a vacuum, is there any air or medium to allow for waves to move? No. No. So in Star Wars, I mean, did it really sound like that? Like, right? No. Sorry to break it to you, but you don't hear those cool things when you're in space, really. Okay. If we look at a cartoon format of what this looks like, we have an outer ear, we have a middle ear, and we have the inner ear. We have these compartments. And this outer ear is functioning to collect these wave signals. The middle ear actually converts them into motion, and this is a membrane. And the membrane is connected to this last bone. And as that bone moves, or actually moves this way, it pushes on the membrane, and that creates a ripple like the pebble in a pond. And that ripple effect moves down that fluid. Now, the middle ear has air in it, and it has the ability to equilibrate with atmospheric air. So this is, when you come down the mountains of Phoenix, or you come up from Phoenix and your ears pop, that sensation, you're equilibrating the middle ear pressure with your outside environment. And this auditory tube, or otherwise known as the eustachian tube, connects basically to where? Back of the throat. Okay? So when we look at sound, and we look at what is it, these are audible vibrations of molecules. And in a vacuum, there's no molecule vibration that takes place. So sound doesn't travel in a vacuum. When we talk about pitch, we're talking about whether it's treble or whether it's bass, whether it's high or whether it's low. The pitch is also referred to as the frequency. And the frequency is measured in hertz. And hertz are basically cycles per second. Cycles per second of the number of waves that travel per second. Bless you. Loudness is also referred to as intensity or amplification of the vibration. And we measure that in decibels. So we'll give some examples of decibel levels here in a moment. So if we look at a different cartoon drawing, but one that's a little bit more anatomically accurate than the first one, we can see really the same main components. We can see the outer ear, we see the middle ear, and we see the inner ear. And the inner ear is sitting within the cranium. And the middle ear also within the cranial space. And the outer ear is basically all of this that you can actually see. Is there a question? Saw that.
What's the definition of hertz again?
Hertz is cycles per second. Yep. Okay, so if we look at the parts of the ear, and we look at the external or the outer ear, we see structures like this auricle. This is this funnel for capturing sound. The earlobe itself. We have the canal, the auditory canal. And the border of the outer ear and the middle ear is the eardrum, otherwise known as the tympanic membrane. So I'm going to give you guys a heads up. There is a quiz or a worksheet question. And it's important for you to know that this is the border. It's the eardrum or the tympanic membrane. No matter what textbooks say, it really is the border. It's not really part of either the inner or the outer. It's the border. On the other side is the middle ear. On this side is the outer ear. Okay? Most oftentimes it's classified as being part of the outer ear. But every now and then you'll see something that says, and controversially disagrees, says part of the middle ear. So it's more accurate to say it's really the border. Okay? When you get into the middle ear, you see these three bones. These are the three smallest bones in the body. Right? The first one known as the malleus, then the incus, and the stapes. The stapes is physically connected to the oval window. The oval window is another secondary membrane, like the tympanic membrane. And when the eardrum vibrates, it pushes on the malleus, which pushes on the incus, which pushes on the stapes, and that pushes on this oval window. On the other side of the oval window is the inner ear. And the oval window is the boundary between the middle ear and the inner ear. Make sense? And then when we get into the inner ear, we're going to see more of a labyrinth that we're going to look at here momentarily. Question?
So, is the eardrum the border between the outer and middle, or middle and inner?
Outer and middle.
Outer. Okay.
Eardrum is the border between the outer and the middle. And the border between the middle and the inner is what? The oval window. Very good. All right. If we look at the inner ear, we're going to see structures known as this oval window that we just talked about. But it's really the boundary. And then we get into our bony labyrinth. And this bony labyrinth is made up of a membranous labyrinth, perilymph, and then also what we call the vestibule. If we unpack this inner ear, we're diving deeper and deeper in. If we unpack this inner ear, when's the last time you guys made cinnamon rolls? Ooh, you're like, wow, how did you just go there? I'm hungry. Okay? So, you guys get them in a tube. Sometimes you can get them in a tube. And then you like, it's like a jack-in-the-box. You like peel off this paper, right? And it's like, press spoon here. It's like, oh, here kids, here, try that, right? And then it goes pop, right? And then the dough like comes out. And they're like in these sheets, depending upon manufacturer, and you kind of roll them, right? And there's a, when they come out, they have like a spiral pattern. So that's really what you're looking at here with the cochlea. The cochlea is a network of tubes that you could unroll, if you were. Right? And if you unrolled it, you'd have this long structure. But to pack that into the cranium, it's a lot easier to roll it up. Okay? So you can imagine, here's our oval window, up here where it all begins. And you can kind of appreciate how this canal system is rolled up. Well, if you take a cross-section through it, you're going to see three inner tubes. And these three inner tubes are shown here. Two of them in green and one in blue. And this is kind of cool. This is how we hear. So you have this upper tube known as the scala vestibuli, and you have this lower tube known as the scala tympani. And then you have a tube in the middle between them known as the cochlear duct, or cochlear duct. And the cochlear duct is filled with endolymph. And the endolymph has potassium as the main ion. It's high in potassium. The endolymph is like the inside of a typical cell, high potassium. Endolymph inside the cell, high potassium. The perilymph in green is high in, what do you think? Sodium, like outside the cell. And so if you look at this diagram, you blow this up in higher magnification, within the cochlear duct, you have this structure. What structure is that? Do you guys know what that structure is called? Anybody read ahead? What's that? Organ of what? Corti, yeah. Organ of Corti, or corti. So the organ of Corti is really our hearing organ. This is where everything happens. So you need to pay attention to this. How do we transfer vibrations or mechanical energy into an electrical signal? Because if you look at the very end, these are fibers that go to the cochlear nerve. Right? The cochlear nerve. The cochlear nerve is going to fuse here in a moment with the vestibular nerve and form the vestibulocochlear nerve, which is one of our cranial nerves. So this is the end game. You know that this is the end game to get it to an electrical signal. How do you go from a vibration of fluid, of those ripples in a pond, to an electrical signal? Well, here's how it happens. Is as the fluid comes down, it travels down this scala vestibuli. And the ripples, the vibrations move down the perilymph in the scala vestibuli. this actually starts to vibrate the endolymph, right? It vibrates this vestibular membrane. That vibrates the endolymph inside the cochlear duct. This ends up vibrating our basilar membrane, which is on this side. And as this membrane vibrates, here's our basilar membrane. Within it are embedded our hearing cells, right? Specifically, our hair cells. Those hair cells are stuck within a membrane known as the textural membrane. And as the bottom moves, it causes mechanical vibration to be transferred to that hair cell. And that's going to trigger, we'll see in a moment, movement of ions, potassium specifically, because inside the endolymph, it's rich in potassium. And that's going to trigger our action potential. Okay? So let me show you this slide, and then we'll kind of review this. Oh, shoot. Where'd it go? Here's our physiology. Okay, we already talked about that. We talked about how the stapes pushes on the perilymph, right? The scale of vestibuli. This moves our vestibular membrane, which moves our endolymph within our cochlear duct. That vibrates the bottom part here, known as our basilar membrane. That causes those hair cells to kind of move, and because the top of them are stuck in this textural membrane, that's causing a gate to open. The gate that opens is shown in this slide. Okay, so do you understand where we are? These are our individual hair cells, stereocilia. Those are these guys up here. Those are these guys right here. You follow? So as we look at an unstimulated state, we can see that the individual hair cells are connected by a protein. This is actually a filamentous protein known as a tip link. You'll see why here in a second. And if we blow up this box right here in an unstimulated state, we can see this diagram. This is a channel. Does that look familiar? That's a potassium channel, because potassium here is high in the endolymph. Remember I told you the blue endolymph is high in potassium. So when this opens, potassium is going to rush in, and that is going to cause a depolarization event. All semester long we've looked at how sodium does this. Here in the ear, we see potassium doing exactly what sodium is doing. As an organism, we could have used any positively charged ion. Right? You could use hydrogen, but it doesn't freely exist really in the body. You could use calcium, but it's used for other things, and that can cause problems. So sodium and potassium are kind of our two preferences. And here's an example that leverages review material of how an action potential works, but with a twist. The twist is the ion is potassium because the fluid that you're sitting in the endolymph is high in potassium. Make sense? Question? Okay. Question, or you're just stretching. So when you push on these hair cells, because they're all connected by the tip link, the link that connects them when they're tipped, okay? All of these guys are opening at the same time and allowing potassium to come in. That causes depolarization, right, on that side, and that's the cochlear nerve. Fibers that lead to the cochlear nerve that interpret now that electrical signal. That's how hearing works. It's super cool. Questions over that?
The cochlea being spiral and getting smaller towards the center, does that help to magnify the sound, or does that just make up function?
Cochlea getting smaller and spiraling. Oh, okay. Next slide. We're going to talk about that right now. Okay. Why the architecture? So pretend that I stretch out the cochlea. That's what this is. You see how long that is? So that's the cochlea rolled out. That's the dough before you're making a cinnamon roll. Before you roll it up. Okay? And as it's rolled out, you can still appreciate the color coordination. We've got our green with our perilymph, and we have our green with our perilymph. Green with our perilymph up top is our scala vestibuli. Our green down low with our perilymph is our scala tympani. Right? Just to prove it to you. Green up top is scala vestibuli with perilymph. Green down below is scala tympani with perilymph. And in the middle is our blue. In the middle is our blue. That's our cochlear duct. Well, you can also appreciate here at the very beginning, at the window, the stapes pushes. This causes a vibration. You can see how it transfers it through to the cochlear duct. That vibration goes to the endolymph in blue, just like we talked about. But not all of the vibration transfers only to the endolymph. Some of it continues down, and at the very, very inner portion, the smallest portion, the perilymph from the scala vestibuli connects to the scala tympani. That's why these fluids are exact, and they do this at this helicotrema. Why? Well, you want to have an ability for that wave to move to our what we call our secondary tympanic membrane. And that absorbs the wave front so that you don't ricochet back a wave and cause an echo effect. Okay, if you drop the rock in the pond, it's really cool until the wave front reaches the shore, right? And then it bounces back and then it gets all messy. So the whole point here is to absorb those waves at your secondary tympanic membrane. And that secondary tympanic membrane is also known as what? The round window. So the oval window is up here. The round window is also what we call our secondary tympanic membrane. And it kind of absorbs that wavefront that's residual, that's left over. It wasn't used to be transmitted to the cochlear duct where your hearing organ is. That's where your organ of Corti lies. It's actually residual. Okay? All right. So if you also look at this, we can see on this pattern in B that we have the ability to hear frequencies in different portions of the cochlea, which is kind of what your question was. So what you can appreciate is our low frequency, right? Low frequency sounds are found at the most, what? Distal end, the free end. And our high frequency sounds are found at the proximal end. High frequency sounds at the proximal end. And then our mid-range is obviously in the middle. So if we were an organism that had a different architecture of a cochlea, you could see how we could expand our range of frequencies that we could detect. There are certain frequencies that you and I can't hear. And as we age, those things get different, right? Do you guys ever try the H test app on the phone with the sound? Has anybody ever done that? It's a little old now, but if you haven't done it, there's an app on your phone that you can download, and it sends out a high-pitched frequency sound, and depending upon your age group, you will lose the ability to hear that high-pitched frequency sound. And so it'll estimate your hearing age based upon whether or not you can hear this tone. So you can try it. If you don't believe me, just try it. And you can test yourself, okay? And so like my kids can hear sounds, and my wife and I are like, that's pretty crazy. I mean, really? There's a sound, right? And it's this really high-pitched sound they can hear. We can't hear it.
Why is there that degradation? What changes in the cochlea?
I don't know. Yeah. Why did we lose our hearing? That's a good question.
Okay,
What? Huh? I don't know. I wish I could tell you. You know, so we'll talk about hearing loss here in a second, but it's not necessarily related to only nerve problems, right? There's something structurally going on. So I don't have a really good answer for you. But that's this question, right? Second to last slide for the day. Hearing loss. So let's kind of talk about what I do know, but I don't know why we lose our hearing as we age. Okay, but it does change. It's modified over time. So if we look at two major types of hearing loss, otherwise known as deafness, we can have things called conduction deafness. Right? Conduction deafness would be the inability to transmit the signal down the canal. You can't conduct the signal. So things like wax blockage, if you rupture the eardrum or tympanic membrane. Otitis media. This is where you've got fluid that's collecting around the ear ossicles. Okay? Otosclerosis. This is where the ossicles themselves, where they connect, they start to stiffen. Like a arthritic type of response that happens between those bones. Those are the smallest bones in the body, and they move a lot. And so if they get more rigid or stiff, you're going to have a loss of hearing. So these are some of the things that do happen with aging, to answer your question. But this happens with aging of all sound, not necessarily just high frequency versus low frequency. Okay? So it is more complicated than this to answer your question, but I don't know the answer to your question. The other one, so conductive hearing loss happens in this, do you see this green shaded out region? This green shaded out region which involves everything of the outer ear and the middle ear. Because it ends, the point right here is right at where the stapes meets the window. Right? And so the green shaded area is all conductive hearing loss, when the sound doesn't reach. Most of the time, these are conditions that can be modified or fixed. We can influence these surgically or medically. Sensorineural deafness happens within the inner ear. And it used to be, even in the time that I've been teaching this class, where we would say that these were non-reversible hearing losses. But that's not true anymore. But what is true is the vast majority of human hearing loss that's sensorineural is due to a problem with the organ of Corti. Let's brainstorm. If you had an individual that was born deaf, or an individual that lost hearing and was no longer hearing, and it was a sensorineural, what are some of the things that could be problematic? Knowing what you know now. Some with the hair cells?
Hair cells will be damaged.
Hair cells are damaged. Perfect. Very common. What else?
Insufficient amount of potassium.
Insufficient amount of potassium. Usually you'll correct that, but that could be more temporary. Anything else? Hair cells are fine. What about the textural membrane? The membrane that the hair cells sit into. That could be never was formed. In some patients, they don't have a textural membrane. So the hair cells do this all day, but because they're not pushing on anything, there's no deflection. Does that make sense? So if the individual never developed in utero a textural membrane, the hair cells can do all the dancing they want, but they're never going to cause a change where the tip link opens. What about fibers of the cochlear nerve that connect to the back of the hair cell? There has to be an attachment there, right? If the hair cells move, you get potassium rushing in, but there's no nerve to connect it to. Do you transmit your depolarization event? No. Now, we used to say that a lot of the sensorineural neuronal are not fixable, but now we see a lot of new technology. Some of you have actually experienced it with friends or family. You've seen people that were deaf that actually can hear. Okay, and so there are cochlear implants that we're putting in patients, right? And they're a device that captures the sound wave, and it sends the electrical signal directly to the cochlear nerve. It bypasses the entire architecture in the inner ear. Our last slide for today, let's talk about these pathways. My hope, stay with me guys, my hope is that this doesn't confuse you like the projection pathway for pain. These are summary slides that hopefully should be putting things together in a stream where you're seeing how this fits together with stuff that we've learned throughout the semester. So for example, here's cranial nerve 8, the vestibular cochlear nerve. Now we've only talked about the cochlea, and we're going to talk about the vestibular apparatus on Wednesday as we finish out the semester. But they fuse. This sends information, right, to the brain, up into various centers that eventually make it over into our primary auditory cortex. But look at a couple of these things that should be familiar to you. Here's our cochlear nucleus, right? And it innervates onto our superior olfactory nucleus, which we didn't talk about, so you can ignore that one. But we did talk about our inferior colliculus. You guys remember the inferior colliculus? The inferior colliculus was the region of the corporal quadrigemina where you hear a sound or somebody yells your name, and you know you can track auditorily where that sound came from. It's because when you get information, it first innervating into that structure to give you that information. And then it goes up into the thalamus. Is that a surprise that it goes to the thalamus? Want to bet that this figure doesn't show all the places the thalamus sends the signal. It's a simplification. So if you heard a sound, a voice, if your mom says your name, Robert, Sean, right? If she says your name, you're like, what's my mom doing here? Right? You would know, or dad, you would know the sound of that loved one because it's in your long-term memory. It went to the limbic system. You guys with me? So you would have a signal that would also go from the thalamus to the limbic centers. But in this diagram, we're sending it to this yellow shaded region, which is our primary auditory cortex. But this should give you an idea of how we're taking all of this information from our environment and we're sending it to the different parts of the brain that we've learned about all semester long. All right, I'll see you guys on Wednesday for our last lecture.